This
Uh,
conference will now be recorded.
Hi,
okay.
Dotan. So for those who we missed the introduction, how about you just start off with presenting today's subject, and we can kick it off from here.
Okay. So my name is Dotan Levi from NVIDIA Architecture Group. We're gonna talk today about enabling time service for a virtual entity, a virtual software entity. Do you see my screen?
Yes, we do.
Okay. So just a recap. Um, we stated from the very beginning, this is one of the slides in a lecture I gave like a few months ago, that we see the accuracy and the stability on as only one pillar of the services that we need to provide as a vendor. And we do see the virtualization as a fundamental thing because we know that the world goes into virtualization. Also, the edge is now being virtualized, 5G is being virtualized. And if we want to allow real-time workloads, enable um, we need to enable time service for virtual software entities. That's about that. And okay, so before I'm going to explain today how we are going to do it in NVIDIA, how we are doing it already. And I will need to explain some of our internals in order to get for you to get the understanding of how it is done, because some things are quite different than the well-known model. And the first one is our clock architecture. Normally in hardware clocks, you have a free running counter that um, um, is theoretically the clock and is timestamping packets and so on. But the timestamp is not a time; it's a number like 4001. And when these timestamps reach to the software, there is some kind of a driver entity that knows what is the hardware frequency and knows when was the epoch time, when was the absolute zero, and translate this 4001 into 9 p.m. on Wednesday, something like this, in a few nanoseconds. Um, that means that um, and okay, let's continue with this drill for a second. If the timestamp was designated to be on a PTP packet and it belongs to a PTP software stack, then the PTP daemon will get the timestamp, get few timestamp, eventually going to understand that there is some kind of a drift in the clock, and he will send an adjust frequency command. This adjust frequency will not adjust anything on the hardware in most cases. In some cases there is, but in most cases it will not adjust anything in the hardware. It will adjust the translations formula in the software. And this is how those things are done. And the problem with that, there are a lot of pros, of course, to that concept. But the downside is that there is a performance impact on any timestamp that you wish to deliver, because no one gets timestamp from the hardware without this driver. We need to mediate it and translate it. Now, in our architecture, since our existing high runner NIC, we change it, and inside the hardware there is the actual PTP hardware clock with a UTC time format. Actually, it can hold any wall clock format that you wish, which means that the hardware possesses the time, the actual wall time in a formatted application knows. When packet comes, the hardware timestamp it with the wall clock format, so you don't need any translation. If it's a PTP packet, then it will go directly to the PTP daemon. The PTP daemon will collect some of those packets, understand if there is a drift, and in our case, it will adjust directly the hardware. adjust frequency, adjust time, and then we get a very disciplined clock. However, all the rest of the application that running on this specific server could enjoy now a scalable service of accurate timestamping. If the NIC can handle 250 million packets per second, then we can deliver 250 million accurate timestamp per second because we don't need any software translation service per timestamp. So when we want to synchronize the host, the most naive way would be to use a PHC to sys because we expose this clock as a PCI device. And there is a Linux service called PHC to sys, part of Linux PTP package. And we configure it to use our clock on the NIC as an origin and the system clock as a target. And there you go. You synchronize your host. Now, we can also synchronize other NIC or other devices if they have their own clock. Any clock that is exposed through the PCI bar can be adjusted in the same way and disciplined. So actually, this is a nice way to scale up and to do and to deliver time synchronization to any software entity because theoretically this application here could also run a PHC to sys if it's running on a VM. Of course, it's flexible and you can do some nice things like this to make your system clock kind of a mediator. All the clocks in the system surrounding him and allowing him to be a master in one way. It's a matter of choice. This clock architecture within the same server will determine how your error bound gonna look like, and it's usually an application or deployment specific requirement. The thing with that is that the software that uses the clock needs to enable the service and run it. So the PHC to sys needs to run in the same security domain and in the same nodes or cores that possess the clock. So if we are running on a VM, each VM needs to run its own PHC to sys. So we're getting a very good accuracy, but we spend some CPU and some would say it's minimal, some would say it's more than what they expected to synchronize the specific VM or node clock. Let's talk for a second about isolation. When we are talking about a virtual environment, one of the main things are that a company, a software develop a package, a container, a software package that is kind of isolated. It should be agnostic to the neighboring software entities that run in next to it on the same platform. It should be isolated in the memory that it consumes. It should assume as minimal as possible on the services that it gets from the system. And with respect to that, one of the options that we see that actually taking the next step and making becoming a trend is that use case where each VM that needs time service is running the entire Linux PTP service, including the PTP4L itself. Now, how could it be? I just explained that there is only one hardware clock. It is possible because this hardware clock comes with some kind of a software layer in the firmware that protects him. And the way that we do it is as follows. There is some kind of a selection mechanism. We are choosing a designated entity. The selection mechanism could be very naive, like the lowest MAC address or the first to come. And it could be sophisticated, like the one with the PTP4L version most up to date, the one with the better sync interval, and many others. But regardless, we selected one, and this designated PTP4L, he doesn't know that he's designated. He's like a king without the crown on its head, and he's of course behaving as normal. He's sending PTP packets, delay requests, and getting syncs from his clock master. And when he wants to discipline a clock, we obey to his commands and we discipline the hardware clock. What about this one, this PTP4L? He of course doesn't know that he is not the master or not the king. He also doesn't have a crown on his head, and he's behaving the exact same. He's receiving sync messages and he's sending delay requests. And when he sends us a discipline command for the clock, we reply, our firmware reply that the adjustment went okay, but we actually are not, we actually don't follow his commands. So we are allowing only this designated one to discipline our clock, and all the rest just we just pretend that they are disciplining us as the clock. As a result, we got a hardware clock which is disciplined and is reliable, because if this one will be teared down, we will automatically select a new one to discipline us. We get a zero phase clock between the VMs because this is practically the same hardware clock. And we get an isolation. None of those software needs to take into a consideration that it's the first, the second, that it's getting the PTP service from from the infrastructure and so on. And yes, there is some kind of a penalty that we need to pay for this, and the penalty is the PTP4L performance and the packets that we send on the wire. But let's figure it out. Those NICs are capable of 250 million packets per second. A PTP daemon would send at most 128 packets per second. You will agree that this is almost nothing um, with those numbers. And with respect to the CPU cycles, um, you must understand that once we run the PTP4L in that format, that we don't need any translation formula. It's no longer a real-time service because the timestamp came accurate directly from the hardware, and even if this service will be stalled, we will not have a major impact on our clock accuracy or stability. And this is why those PTP4L daemons should not be, we don't recommend them to be isolated for a dedicated CPU core. They could run on any other core. They will consume less cycles because they don't have the translation real-time requirements, and they will not occupy a full core. So this is one way, using those scalable isolated PTP4L and using the PHC2Sys. I should have done another drawing showing that the PHC2Sys is also running for each VM, and so on. So I'm going to move now to another method that we allow, but I'm wondering if there are any questions in the crowd for that.
Hi, Dotan. Quick question. So, can you talk to the pros and cons of each method, and how are we seeing the market going?
You mean with respect to the non-real-time clock on the hardware, or because I haven't we also have another method. I didn't explain yet the second method, but maybe you are referring to the different
Yeah,
architecture.
go over the methods and then describe.
Okay.
Yeah. Yeah, correct.
So
But you can finish with a different method.
okay. Any other questions other than that? Okay. Yeah, we can do the same for multi-host, by the way. This is OCP server that has multiple CPUs in one server and only one NIC serving them. And we, of course, follow the same architecture and it works pretty fine. Okay, in order to explain the second method, I want to emphasize that the fact that we have a real-time clock inside the hardware, here it is, give us some flexibility that we didn't have in the past. Since the hardware knows what is the actual wall clock time, we can theoretically develop a whole new semantics of network commands or hardware commands that are time related because the hardware and the application have yet another language to speak with, the time axis. Um, the hardware knows what is 8 o'clock, the hardware knows what is tomorrow, and so on. And that's what we did. I mean, this is not a yesterday design. It is a couple of years ago. And we have a way to dictate the hardware to send a packet at a specific time. So if we want to send packets at a specific time, um, we have a hardware command to tell the hardware to get those packets, not to take those packets before a specific time will come. Of course, we arm those software queues with the right privilege and the right priority. And once this fence will reach the time barrier, those packets will be sent, and this is very accurate and scalable. And it uses use cases for 5G and such, but this is not what I wanted to talk about. I wanted to talk about something we called a clock queue. Let's do a theoretical experiment. We're going to take a software queue, we're going to put packets, and we're going to place time fences every second between them. So we have like 2 million packets in a queue and wait for some second, and another 2 million packets with another fence, and so on. And we also connect this queue to a packet pacing format. Packet pacing is a mechanism that allows the hardware to enforce a very fine and accurate bit rate, fine in a matter of inter-packet gaps of nanoseconds. So we can, for example, tune the hardware to send packets every 500 nano. This is not our top boundary, but I'm using this example for this case because 400 nanoseconds per packet means 2 million packets per second. So if we put this fence in 8 o'clock, for example, and then we took 2 million packets, those packets will be evenly spread on the next second. Now comes the funny part. The packets are null. We don't put anything in the packet. We are actually sending packet with the length of 0. So why do we do that? There is some kind of a byproduct because for every packet that we send, there is a notification descriptor that being created and being sent to the software, which means that not only a packet is being sent every 500 nano, also a completion notification is generated every 500 nano. And a completion notification is populated into what we call the completion queue. And this is how software, for example, in high-speed networking knows that the buffer that containing the packets could be evacuated because those packets are already being sent. If this is a transmit flow, and if this is a receive flow, this completion notification indicates to the software that the packet actually arrived and you can access the data. And software is doing polling on those queues normally in high-speed networking. Okay, so what we have a queue with packets with size 0. So the queue contain only commands to send empty packets. Those commands are being consumed every 500 nano and generating a notification every 500 nanoseconds. So we get notification, notification, notification. Another nice thing is that the notification carry the timestamp. And since the timestamp, as we said, is the wall clock format, this is actually the actual time that the non-packet was sent. Now, there comes another feature in the hardware that we use for our supercomputer market. It's called completion notification collapse. And it's a feature that exists on our NX for more than one generation, and it allows us to write the notification command without incrementing the address. So actually, notification number 2 will be written on top of notification number 1 in the same address, and so on. So this queue will be actually in the size of 1. I'm not sure if you are following where I'm going, but here comes the twist. Since these notifications are 50 nanoseconds equally spreaded, and they contain the timestamp, and they written one on top of the other, there are 64 bits in that address that actually creating a clock. Yes, it's a 500 nanoseconds square step clock, but this is a clock that the software has nothing to do in order to get it. The NIC generate this clock in the software user space. So what we could do, and we are doing that in some cases, we are putting those software queues in our firmware because this is dummy packets, and we are generating completion notification to user space application. So every application that will come will get those, and it registered to this service could get this real-time user space clock, and this will consume 0 CPU from the software side. Questions?
I'd like to ask you about the notifications. You said
Yes.
0 CPU. What does that mean? How
means
does
that-
the application consume this notification?
Okay, leave the consumption for a second. Just for the sake of the generation of this notification, the CPU does nothing. This is a PCI transaction initiated by the network adapter.
Okay.
Only when the CPU wants to read the time, it just read it like any other space that it has. It doesn't need any mutex. It doesn't need any context switch. It just read the time. That's what I meant.
Okay, thanks.
Okay, so actually now we kind of having a trade-off. We have two ways to consume time service in a virtual entity. Let's name one of them PHC2Sys, which is standard. It's very much accurate, and but the downside that it's costing some load. And for those who need this accuracy, this is the best practice. But if you don't need that much of an accuracy and you only need 1 microsecond, of course, this could be improved in the next generation of the hardware. The clock queue is a nice alternative. It will be less accurate, but it will require much less load with respect to the CPU resources. There is a comment here. The clock queue mechanism consumes resources on the NIC size. For every clock queue that you will populate, the NIC will have to deal with 2 million packets. So out of 250 million packets per second, we lost 1% of performance. And very least use cases.
1% at 1%.
It's not 1% of. Yeah, it's not 1% of the bandwidth. The NIC has several. Each network adapter has several bottlenecks. It has one bottleneck which is the PCI bandwidth. One bottleneck is the network bandwidth. and one bottleneck is the number of packets per second that it can pass in each direction. And this specific NIC, let's assume it can handle 250 million packets per second in each direction, and each clock queue will consume that resource, only that. The bandwidth will be minimal because those are 64 bytes times 2 million, so the bandwidth consumption is less than 1%. But on the packets per second, this is a consumption. Again, from application point of view, it doesn't consume CPU.
Excuse me, I have actually one question.
Yes.
So the clock queue, you mentioned that the reason that we have the time because the timestamps of the notification is coming to the clock queue, right? And my question is that does the PCIe latency change the accuracy of the clock queue?
This is a good question. So I assume, let's go over PCI for a second. Let's talk about this service. PHC to sys is actually depend on the accuracy of PCI read. PCI read is a complicated transaction because it requires a round trip transaction on the PCI. And since the PCI, when the system is loaded, is extremely jittery, what this PHC to sys is doing, it is doing a multiple reads per command, and it takes the minimum one. I think the procedure is something like it reads the time on the PHC, reads the time on the system, and then reads again the time on the PHC, and then repeating this 5 times, and then taking the one with the minimal distance between the PHC samples, which indicates that this was the lowest latency. And it correlates the time of the PHC to the middle point between those. It correlates the time on the system to the middle point between the PHC readouts. However, in that operation, this is not PCI read. This is PCI write. So and we can even implement it as a posted write, and we can even relax the ordering to reduce the jitter. So all in all, I think this method is less. Yes, it is affected by PCI jitter, but less than the PHC to sys. But regardless, accuracy is not the strong side of this method. This method is used to allow you some scalability with zero cost. It's less accurate than this one.
I see. And do you have any any estimate of what would be the accuracy of the write? What's the jitter range?
Yes. So in PHC to sys, I think we try to stress our system both in the CPU size and on the NIC, and we reach the maximum that we reach is 250 nanoseconds between the system clock and the NIC clock. And with that, this go all the way up to microsecond.
Thank you.
Elad, it went quite fast. I was hoping to get more questions, but I'm practically done.
I get it. Okay. So this has been definitely a new direction we have not yet touched in our TAP sessions. And it should speak to a wider audience and to how we are going to scale our software.
Let me ask a few more questions.
Go ahead,
Sure.
Gogi.
Yeah. So the slide shows how we propagate the time from the NIC to the Docker containers or the VMs. I was wondering if we can do this only once to the hypervisor, and hypervisor can expose some kind of read-only shared memory that allows reading this data, wouldn't that be more efficient and shared between the containers and VMs?
Well, first of all, I'm not a software expert, but I can say that from my point of view, for the sake of isolation and the fact there is an advantage that each one will get his own time service. There is the NUMA thing. If and our new systems are multi, they are not they are not non-linear memory latency. You have dual sockets sometimes, so you can populate this in a closed memory. By the way, our network adapter and not only ours contain technology of cache snooping. So if the application reads this time regularly, we can assume that it will be cached. And those our PCI transaction, when they indicate that the address is cached, we are writing directly to the third level cache. So we are trying to, I think there is a value to bring the information closer to the app. If what you suggested is doable and doesn't change much the parameters that I described, maybe it's something that worth considering. I know that from security point of view, it's maybe a problem. You need to expose like a memory region for all, just for read. So I'm not sure if you can do that. You probably know better
I'm not
than me,
sure either,
Georgie.
and I believe it depends on the hypervisor, but I also expect for some of the existing systems, the hypervisor to do this operation when low latency is the goal, because the transitioning between a hypervisor and the client, there is some cost of this.
Mhm. Yeah, I know for sure that. Yeah, sorry.
How many clients can we support through the queue?
Our existing use cases, maximum case at the moment is 16.
16.
I don't think we can go much higher.
And because a limit of the NIC, we are going to exhaust some resources on the
Yeah,
NIC.
yeah. In the next generation, we have some way to multiply just the notification into different addresses, and that would be a bit cheaper than it is today. But today, every clock you consume is on resources.
Mm-hmm. Okay, thank you.
Dotan again. So I was going to ask, and maybe it's a little bit premature to ask, but how do you view TAP's role the TAP's role in standardizing and the software APIs for a virtualized environment? Where do you see a gap in the implementation, and where we can collaborate as a community?
Yeah, I think it's a great one, great question, and that will definitely we will deal with in the next year. We set the foundation for what it's needed for time service at data centers at the very early days, and I think if we look back, we didn't made too much mistakes. We understood from all the beginning that reliability and the scalability and the observability are the most important things. And I think that I think this got a very good feedback from Google um, 6 weeks ago or something. Sundial, interesting paper.
Right.
And I think that, yeah, and I think that once we will establish all the missing steps towards a reliable clock, and from my point of view, the missing part is the security thing. I think we're gonna see that there will be a demand to do real-time workloads in the cloud because this time service will be democratized, as we say. It will be available, and we will need to find a language to tell the application what are the characteristics of the clock. We will need to populate almost immediately when the clock is out of sync. We will need to tell each application what is the error bound that it can assume, and we will need to develop the API for that. I think that's our challenge in the post-security step.
I see. Thank you. Yeah, and there are the question was kind of directed because we are looking to establish a new work stream that will deal with fault tolerance and
Yeah.
these aspects within TAP, and these are.
Yeah, I think this is. I think we want to address those call for action for the people here that are part of a bigger company that also has application development within the same companies. Please, guys, spread out the rumor. Time service is available at clouds. It's going to be available at enterprises, and we need to find use cases, and we need application guys to visionary the requirements and to help us define the interfaces.
Yeah, this is definitely the call to action, and we can Dotan articulate that in our mailing list and to see that we are touching our wider community.
Mm-hmm.
Okay, that's great. Let's see if there are other questions, guys. Please open your microphone. Hisham, you're very quiet. Okay. So
Okay, I think
again,
Dotan,
Dotan.
it's okay a lot from time to time not to go over the hour.
Yeah. So again, thank you, Dotan, for this session. You were with us as a founding member from day one with the initial vision, and I think this is definitely the next big milestone for us to watch at TAP. So thanks for today.
Thank you.
And we
Bye-bye.
will see you all at this summit next week. Bye-bye.
Bye-bye.
Thank you. Thank you.